we are here at the second fall journal club meeting, and we have Thomas Stiadle with us today. He works with Alan Bayless and Wolford on the side math department. You're muted. Hi, today is the second journal club of the fall quarter, and we have Thomas Stiadle from the Applied Math department, who works with Alvin Bayless and Wolford on population dynamics and things like that. But he's not going to talk about that today. He's going to talk about Julia, which is considered to be the future of scientific computing because it's as simple as Python and as fast as Fortran. So it was developed at MIT, and it's been getting popular the last 5 to 6 years. And many schools have started using Julia in their programming syllabus. And we will expect to see it grow in the next few years. So this is a very useful tutorial to know. Now over to you, Thomas.
Thanks. All right, so let's see if I can do this whole Zoom thing correctly. I'm like one of those now. Where did this go? Oh, there it is. Look at that. All right, we'll just share the whole thing. No. Oh no, we have to show the whole thing because there's some there's some interactivity going on here, right? So okay. So this is a very, very, very brief and not at all exhaustive introduction to Julia. So first of all, what are we even talking about? Julia is a dynamic programming language. And if you don't know what that means, that's okay, because we'll talk about that in a minute. And it was designed largely with scientific computing in mind. And when I say that, what I really mean is performance is important in Julia. But at the same time, they didn't want to do the same kind of thing that Fortran and C do, where they're annoying to use. So the whole idea behind this development was balancing performance with simplicity. And even better than that, it's free and open source. That already puts the notch above MATLAB because that is neither of those things. All right, so we're going to go through 6 what I would call big advantages of Julia. The first one is that it is easy to use interactively. So it features an interactive command line, which is known as REPL, which stands for Read, Evaluate, Print, Loop. And it does exactly what it sounds like it does. It allows you to just input commands directly. It allows you to easily run scripts. So in that sense, it's a lot like the command line that you have in MATLAB and in other languages. I believe for many IDEs, Python has one. I know R has a similar type thing. Yeah, but it's very nice, to kind of check on what you're doing. So let's see, for example, if we go in here and we open this thing up, we can just start typing in commands directly. So for example, we can take a variable X, we can set it equal to pi, and then it'll be like, okay, cool, now X is pi. We can find the sign of X. We can set Y equal to 4. We can define complex numbers using the imaginary variable, which here is IM, which is nice because it means that it frees up I for indexing, which is a problem in some other languages. We can do the usual arithmetic. We can make some strings. Cool. And we can very easily run scripts directly from here as well, through a shell command. So for example, if I have a file, if I have a script called hello, which I do, funnily enough, then you can just run it by typing the command Julia and then the name of the file. So in this case there, and then it'll give you, it'll execute the program for you. The other nice thing is that similar to a lot of the more popular languages, there are very easy to use packages for plotting, which I know everyone likes to do. So for example, if we wait for the plot package to load, and while we're waiting for that to load, I will mention you're like, wow, this is taking forever to load. Like, I thought you said this was fast. It does take forever to load plots. A big reason for that, and with certain other commands, is that the one knock on Julia is it does have a lot of overhead. So it's not so good necessarily if you're trying to get a very quick answer to a very simple problem. In those cases, other languages like even Python could outperform it because it prides itself on not having all that overhead. But yeah, but if you're doing a bunch of things over and over and over and over again, you don't care about overhead. So there's that. Okay, so let's see. Let's define a range for x. Oops. Let's set y equal to x, and let's set z equal to x over 2. Okay. And by the way, before I go on, I would like to mention that if you give a command and end it with a semicolon, just like MATLAB, it'll suppress the output so you don't get all that annoying junk in there. Okay. And now if I just go in and say, okay, cool, let's plot y against x. We'll again wait for a minute because it has to open a new window, and you know how that goes. But eventually it'll come up. Eventually. Someday. Any day. Watch my computer just like crash or something. That'd be wild.
You have to do like PLT or plot or something like that.
You do not. No. Okay, there we go. Yeah. So that's one advantage over Python. Like a lot of the commands are simplified. Like once you load the library, you can just use the library directly. You don't need any of the precursor type stuff in front of the command.
But suppose you have plot defined like in different ways, you know.
Yeah, so yes, then you would have to specify. Otherwise, there are rules for which one it defaults to. I don't remember those off the top of my head, but yeah, no, that's a good question. And we'll actually talk about that a little bit in a bit. Okay, yeah, so this just gives you like a quick plot, right? And you're like, okay, but this, this plot looks kind of crappy, right? Like, how do I, how do I use like, the good plotting software, right? Well, first of all, before we get into that, I would like to note that, how that took forever to plot? Okay, now that I have it here, it won't take forever to plot. So for example, if now I want to plot Z as well on the same set of axes, that's pretty much instant, right? So that's what I meant with like the overhead sucks, but everything else is pretty smooth sailing. All right, now in terms of making things look nice, I can use a different back end. So for example, I can use PyPlot, which is everyone's favorite, except for mine. And then once again, wait a second. Okay. And now it's loaded the Python backend. And now I can go ahead and, for example, plot something in 3D. Like that. And once again, it will take a hot minute to load. And again, so ideally, because of all this overhead, what you want to do is at the beginning of your session, you want to pick a backend and you want to stick with it. So, find your favorite one, go with that. Any day. Okay, there we go. Okay, so now I have, now I have a nice little 3D plot here, right? And then, surfaces are just as easy. Like, let's say I want to define the surface F by just the sum x plus y. I can do almost the exact same thing I did before, except give it the surface attribute. And now it will give me a surface. See, pretty and all that. And then, yeah, in terms of all the labeling, title, legend, all that kind of stuff, the commands are very, very similar to MATLAB. So yeah, if you're interested, you can go look up the syntax for that. But yeah, it's very straightforward, especially for simple plots like this. So, okay. Cool. So that was one thing. Now, next advantage is the language is dynamically typed. And what we mean by that is, first of all, you don't need to explicitly type anything. So, this is similar to languages like Python, MATLAB, and so on, where, people are like, types, what are those? Additionally, you can have types change when required, whether that's through promotion or whether that's just through redefining a variable, whatever it may be. That's all fine and good. Generally means that you need less code because you don't have a whole bunch of declarations at the top of your code, and you can reuse variables a lot more easily. However, and this is a big thing, you can specify types if you want to, and you can hold variables to those types. And the reason that can be nice is that it can drastically speed up your code in certain situations. Like if you know that something's going to be an integer, just say it's an integer, right? And what's also nice is that you can take advantage of type hierarchies, and we'll get into what I mean by that in a second. So if we look at some of the types we've already defined, let's say we take y equals, let's say we define y equals 4 again, we can back out what type y has with the type of command, and we can see, okay, it's an integer, right? 64-bit integer, cool. I didn't declare it as such, but I just saw it, was like, yep, that's an integer, called it an integer. All right. And if we look at let's say w equals 5 plus I, and we take the type of w, that'll say, okay, it's a complex number made up of 2 integers, right? So, okay, so that's all very straightforward. It's very similar to typing in other languages that use it. But now, what's nice is that even though y is an integer, if I tack on a real number to it, now y adjusts and becomes a real number, right? And this isn't anything crazy. It's the kind of thing that happens in Python. It's kind of thing that happens in MATLAB and so on. But it's the whole point of this is, yes, it's a dynamic language. This still works. And then, even though like y is now a real, if I go back and set equals something like 12, now it's back to being an integer, right? So it works both ways. All right. Now, where explicitly typing things can be useful is, let's say I wanted to compute the dot product of 2 vectors. So let's call one vector x, let's call, say 1, 2, 3. Let's say y is 4, 5, 6. And then let's say in order to compute the dot product, I want to import my own super special secret library, which isn't really a library, it's actually a module. To do that, I would just include the name of the module, which is secret math, because it's secret. And then I need to tell it that I want to use it. All right. And now I can go ahead and compute the dot product. So I call, in that module, I have a function called compute dot, which does exactly what it sounds like. And you just stick an x and y, and it gives you the dot product, right? Now, the thing is, though, what if I stick something in there that's not a number, right? Or like, what if I stuck in two vectors that weren't just made up of integers, right? Like maybe I would have a different routine to handle each of those cases. So for example, if I leave X the way it is, but now set Y equal to some string, right? And then go ahead and try to compute the dot product, you'd be like, oh, it's going to throw an error. No, it won't throw an error because I have a way to handle this. It'll be like, no. You can't stick a word in the dot product, right? Okay. And so the reason that this happens, if we go into the actual module here, so what you'll see is I have two functions that are called the exact same thing, right? The only difference between the two are in the inputs. So, okay, in this first one, I say there are two inputs, dx and dy. They both have to be vectors, and they both have to be vectors of type t, where t is some descendant of the type that's just called number, which includes things like, reals, integers, complexes. Huh? Can I zoom in? I don't know if I can do that. Yeah, is that better? Okay, so that's all fine, good. So basically, okay, if it meets these criteria, then you use this function. If it doesn't, then you use this other one where I say that the inputs can be whatever you want them to be. And this designation of any isn't required, but I stuck it out there to be more explicit. And yes, this is a very stupid example because, you can just be like, well, yeah, just like don't put numbers in there and have it throw an error and that's fine. But for things that aren't as simple as a dot product, like, say you're looking at matrix decomposition or that kind of thing, it might be good to know what kind of data you're working with, right? There might be some way to optimize. And so by defining functions like this, which, technically would be called a function with multiple methods, you can optimize your code for whatever case you happen to have. So that can be nice to do. Okay, moving on. A third advantage is that Julia actually does compile its scripts rather than interpreting them. This is different from most dynamically typed languages that you're used to, like MATLAB or Python, but it's one of the big reasons for the speed up. And it turns out that compilation occurs at runtime rather than before. That's what allows for this nice interactivity. C and Fortran, not so much, as I'm sure many of us are familiar with, because yeah, you've taken HPC, right? Okay, yeah, you're familiar with that. All right. And then just to give you an idea of what I mean by that, here are a number of routines that are used as benchmarks for different languages. And yeah, it's kind of hard to read, isn't it? Let's see if we can zoom in a little bit. And so you'll see that Julia is reasonably robust, right? It does a lot of different types of routines very quickly. It's not the best at all of them, but it's certainly not the worst at any of them either. You see that Fortran is similar, except Fortran's a lot faster at certain things because Fortran's great, right, everybody? Yeah. And then, then we come over here to your more modern languages, I guess you could say. Like, yeah, MATLAB kind of sucks. R is not so good. Python, depends on what it is. Oh, and by the way, all this is normalized to C, in case you're wondering where C is. So yeah, this just shows, even though Julia you would think of as being more in this kind of category over here, it's much, much faster in general. That was too far. Okay. Fourth advantage is the syntax is not very annoying, at least in my humble opinion. It is optimized for math, which makes it very nice for mathematicians who don't want to sit there and, figure out all the CS stuff, as opposed to things like, Fortran and C and that kind of thing. It's particularly nice for machine learning and linear algebra, everybody's two favorite things, especially when you compare it to Python. Once again, in my opinion, but I think it's a pretty objective opinion. And yeah, and what I mean by that is, especially for linear algebra and that kind of thing, it's very similar in terms of convenience to MATLAB. So for example, there's a library called linear algebra, which is very aptly named. And you can sit here and define a matrix just like you do in MATLAB. Here, I won't suppress this. You can see it even writes it out nicely for you, right? I can find, I can still use the backslash operator and it'll give you an answer. I can find the LU decomposition. I can find the QR decomposition. I can find the SVD. I can find the eigenvalues, and so on and so forth. Maybe I can find the eigenvalues. There we go. Yeah, and so a lot of these commands are very similar to MATLAB, and that's not an accident. It's just because these are commands that are they're very sensible, very convenient. But once again, this is free, and MATLAB is not. And yeah, I don't know how many of you have tried to use Python to do any kind of linear algebra, but it's not so good. All right. Fifth advantage is what we're going to call memory management. Just like Python, you don't need to worry about allocating or freeing memory. Unlike in say C or Fortran, where you have to sit there and be like, allocate this, allocate it this way, and then when you're done with it, you have to tell it to not do that anymore. But you can still do that if you want to, for whatever reason. Perhaps if you're doing something in parallel, you might have a reason to do it. Perhaps if you don't trust computers, you might have a reason to do it. And it turns out that parallelization, that's a word, is reasonably straightforward. And there are several options for doing so. And, in my opinion, they're all not bad. You can do multi-threading, distributed computing, GPU computing, and so on. And, I feel like objectively, they're all easier than their counterparts in C. So just like a very, very quick example of that. Let me actually back out here and go back in. If you want to load Julia with multiple processors, you start it with this -p for processors, and then the number of processors you want to use. And then they'll start, and they'll be like, wow, now you have 2 processors. Okay. So just like a very easy thing I could do is I can have a random matrix be generated on the processor I'm not on right now. I can do that with this remote call function. And what you do is you just say remote call, and then you give it the command that you want to happen on some processor. So I want the rand command to happen, which is just like it is in MATLAB. And then you say, I want it to happen, I want it to happen on process 2. And then you give the inputs to rand. And in this case, I want a 2x2 matrix. So I'll just do 2 and 2 again. Okay, and I do that. And then on the other processor, it will generate a random 2x2 matrix. Okay. Now let's say I also want another random matrix called Q also to be generated on another processor. Okay, so I have 2 random matrices on the other processor, and now I need some way to bring them over, right? Okay, so but let's say before I bring them over, I want to add them together. So in order to add them together without bringing them over, what I need to do is add them together on the other processor. And so what you do is we'll call the sum s, and we'll use this nice macro called spawn at, which does exactly what it sounds like it will. The identity of the processor, which in this case is 2. And then you tell it that you want to add Q and R, but Q and R are not just, variables in the usual sense of the word, right? So what you have to do is you have to fetch them. So I want to fetch Q and I want to fetch R. And then what happens is over on the other processor, S is now the sum of those two random matrices. Okay, and then finally, let's say I want to know what that sum is. Now I can fetch S, bring it here. There we go, there's S. So obviously this is a very stupid example and you would never actually do this, but it just goes to show like this, this is technically distributed computing, right? And there was no direct calls to MPI or anything weird like that. Like, this is all reasonably straightforward.
When you're doing fetch,
yes,
does it know where to fetch it from?
It does.
Does it know that Q is on 2?
It does.
Or does it have to search for that again?
I'm not sure when or if it actually goes through a whole search. I doubt it, but it knows that Q is on 2 because that is where I called it to be, if that makes sense.
Like, does this spawn at 2 give it the or
No. So the spawn at 2 is saying I want that addition to happen on the second processor. Yeah, it says nothing about the location of Q or R. Yeah.
What is like R referencing on the first process of Q? Like a not looking thing, or like that's only defined in the namespace for the second processor?
That's correct. Yeah. Yeah. So like if I were to just say R, it'd just be like, yeah, it's somewhere,
Okay.
but yeah. Yeah. So like, I mean, you can kind of think of it as a pointer, right? Like it's like, yeah, it's somewhere, but I can't directly get it until you explicitly tell me to do that. All right. All right. And then the final advantage, which I think is the absolute coolest thing about this language, is that you can directly use libraries for C or Fortran or Python if you want to do that for some reason. And it's theoretically possible to exchange data directly between Julia and Python. I haven't personally tried that because I don't really use Python, but if any of you who are better at Python than me want to take a shot at it, be my guest. It's apparently not too bad. But yeah, so for example, if we go into Fortran, let's say I have a function over here written in Fortran that all it does is just return 1, right? It does nothing else, takes no inputs. It's the worst. What I can do is if I compile this function into a shared library, which I've already done, then what you can do is if we go into Julia, we can use this special function calledccall, which stands for, call from C, except in this case it'll be Fortran because that works too. And the syntax is as follows. You put in the name of the function that you're trying to call, which in this case is useless. You put in the location and the name of the library. So in this case, just bear with me. Oh, I remember where I actually put this thing. I think it's called that. We'll find out. Okay. And then the second argument that goes in here is the data type of the return value, which in this case we'll say is an integer because we know that that's what it's going to be. But I wouldn't have to, right? I could say something more general than that. That'd be fine. And then the third thing you put in there is what the arguments of the actual function are going to be. And in this case, there are none, but you still have to put something there. So yeah. Okay. And then you go ahead and run it. And then there's the result of the function, right? So yeah, didn't have to do anything, didn't have to, redefine anything. It's, it's pretty painless. A more interesting example of that is, let's see if we do something that's actually real. So, okay, let's say I go into my very extensive Fortran library, which is very extensive. And let's say I find the easiest looking thing I could find, which was at some point, I apparently felt it was necessary to write a solver for finding the root of a cubic polynomial. I really don't remember why I did that, but it happened at some point. Anyway, so the point is I have this function which relies on a bunch of other functions, and I compiled all that into a library. This function takes in 7 values. A, B, C, D are just the coefficients for the cubic. Tolerance is the tolerance for either Newton's method or secant method. Z0 is your first guess at the root. Z1 is your other guess if you're using the secant method. And okay, if I wanted to, run this thing in Fortran, I could certainly go ahead and do that, right? I'd have to make a driver program. I'd have to compile all that, link it to the library, so on and so forth. It can be done, and it is done, but it's annoying. On the other hand, if I call it from Julia, it will still be annoying just because there are a bunch of inputs, but it's not that bad. So for this one, I want to call the function cubic root, which is in the same place as before. This time the return value will be a float. And now here, this is where it's a little bit more annoying. Here, I need to put in the types of the arguments. And it turns out for Fortran, you have to wrap those a little bit. So for C, I could just write, let's say my first type is a float, right? For C, I could just do this. I could just say, yep, float 64 and just so on and so forth, right? For Fortran, I can't do that. I have to put this reference in front of it, but it's fine. And you just repeat that for as many inputs as you have. So in this case, we have 7. So I have to type this out 7 times. Yeah. And obviously, in general, you would not be doing this on the command line. You would set this all up. You would probably just wrap it in a Julia function itself. Yeah. Okay, but okay, cool. Now I've done all that, and then I just have to put in what those inputs actually are. And now notice, because of the automatic widening, right? I don't actually need to type things like 1.0, 0.0, so on. Even though they're supposed to be real numbers, I can just get away with using integers because it's fine. They'll be widened. So I don't know. Let's do something like that, I guess. Okay. And then it should just, or not, because I spelled something wrong. Oh, because I used the wrong library. Whoops. There you go. Okay. Yep. And then there's the answer, which is exactly what you would get otherwise.
Can you do instead of 1, 0, 0, 0, 1, 0, 0, 1?
Like that? Sure. Yeah, it probably doesn't fit because the guess is wrong now.
Make the guess.
Do you actually know where this root is? Thanks. There you go.
But make it -0.8.
What, here?
No, before, at the end, the guess.
I hate this. Thanks. No, like, yeah, like I know that works. Like that wasn't the point of this. All right, and I'm pretty sure that's the end. Yeah. So any remaining questions? Yeah, so to my knowledge, it's not very good with symbolic algebra. I mean, like there is a library for it. I'm like 99% sure, but it's, let's be honest, it's kind of like the library for MATLAB. Like it's like, yeah. So yeah, I would highly recommend symbolic algebra. Like Mathematica and Maple are like in their own tier. Like nothing else is even remote. Yeah. Like for as much as we all complain about Mathematica, like it's actually pretty good. Like
Thanks, Thomas, for giving a great talk.
yeah. Success.